Okay, hey, hello everyone. Okay, so what I'm recording here is just a quick video showing you how to run a one-way independent groups MANOVA using SPSS. And I'm using the data file that we will use in the lab class, the worksheet data file we'll use in the lab classes in week 15. It is a data file with a number of variables. It's got age group, which although it's shown here as a scale variable, is actually a categorical variable with 1, 2, 3, 4 levels. Okay, and if we look at what they are in variable view, we can see that group, if it's group 1, it's people aged 20 to 30 years, group 2 30 to 40 years, group 3 40 to 50 years, group 4 50 to 60 years. Okay, so a categorical variable, although it isn't shown as such, we can maybe change that to categorical variable. Okay, there we go. The others are scale variables. The first one is subject number, which is just a participant ID number. We have got altogether, let's have a look, 451 participants in this data set, and we've got a number of other scale variables. One is called physical health, heal physical health, and it's a count of number of times someone has attended a doctor. We're reporting some sort of physical health symptoms, and I believe this is the kind of health data set used by Tabashnik and Fidel in their textbook. Mental health, which is number of mental health symptoms that a person has attended a doctor's or reported to a doctor in a given year. Drug use, which is use of drugs, use of psychotropic drugs in particular, I believe. Yeah, if you look at the label here, use of psychotropic drugs, so stuff that's not necessarily prescribed. And the last one is stress, and this is number of life-changing events, stressful events in their life in a given year. So higher scores mean more stress. Okay, and what we're going to do is do a MANOVA on this, where we're going to use our one categorical variable as the independent variable, that's age group, and four scale variables as dependent variables. Okay, so to set this up, it's pretty straightforward. We click Analyze. We go to General Linear Model, and in previous occasions, we've kind of used univariate, but this is obviously a multivariate statistical test. We've got multiple DVs, so we're going to click on multivariate, and it brings up a very similar box to if we ask for a univariate test. What we're going to do is we're going to put age group as our independent variable in the fixed factors box, and then we're going to put the four variables that we're interested in as dependent variables in the dependent variables box. So we're going to use physical health symptoms, mental health symptoms, use of psychotropic drugs, and stress for life events in the dependent variables. So we've got a reasonably complex design here. We've only got one IV with 4 levels, but we're looking at a combined dependent variable where we run this MANOVA on 4 different dependent variables. Okay, so a couple of things to look at here. We're not going to ask for too many things because it already gives us lots of output. If we click on options, we can ask for descriptive statistics and homogeneity tests. Okay, we've got an independent groups design, so we want some homogeneity tests. Certainly for you, we do some univariate ANOVAs, we'd like some Levine's test. It will already give us boxes M test and things like that when we run this. We're not going to select any, but I'll just select it to highlight it. I'll just show you to highlight it. We can also ask for post hoc tests. So if we moved our post hoc tests over there, we can select a series of post hoc tests, whatever we might like. Should we get a significant MANOVA and then want to do some sort of univariate ANOVA test, and then post hocs on those, so we could collect Bonferroni or various others there if we can't assume equal variances. I shall put that back for now, and we should just click continue. And that's it essentially. If I click OK, run this analysis. Let's make the window bigger. So you can see the first thing that we get here is this between subjects factors. It shows you the 4 levels of our age group variables. So 20 to 30, 1, 2, 3, 4, 20, 30, 30, 40, 40, 50, 50 to 60. And you can see there is some variation in the numbers in each group, but they're all over 100 and they're roughly similar. So that's quite useful to know because it shouldn't cause us too many problems. And then it gives us descriptive statistics for each of the dependent variables, but broken down by age group, by the different levels of the independent variable. Okay, after that we've got Box's M-test right here, so its own table. And if you remember, this test for the equality of variance covariance matrices, so it's testing to see whether it's kind of like a generalized equality homogeneous variance test, but for our variance covariance matrices, because we're doing a multivariate test. Okay, and it gives us a Box's M value of 54.145, and it gives us a significance of 0.006. And we might jump to the conclusion that that is significant, and we can't assume equality of covariance matrices. But if you remember in the lecture, I mentioned that it's a very sensitive test. So the recommendation is that you adjust the significance level down so that we're not getting significant results when the differences in variance between the matrices are quite trivial. And the recommendation is that you adjust your significance level down to 0.001. So anything above 0.001 would not be considered a significant result. Anything below that, anything smaller than that would be. And in this case, you can see 0.006 is bigger than 0.001, so it's not significant. So we are, in this case, probably safe to assume equality of covariance matrices. Okay, so with that done, we could then just have a look, see if we do have a significant MANOVA result, and we'd look at this multivariate test table. And as you know from the lecture, it gives us 4 different ANOVA results. We have to choose which one based on what our data looks like, which assumptions are met, how many levels we've got, etc. In this case, we're pretty confident we've met the assumption of homogeneity or equality of variance covariance matrices, so we could probably be safe to report Wilks lambda. Okay, so Wilks lambda is pretty good when we're pretty confident all our assumptions are met. So in this case, we've got an F value of 4.879 with 12 and 1175 degrees of freedom. P is less than 0.001, so we could safely, in this case, report Wilks lambda as our MANOVA F statistic, and we find we've got a significant result. So what that means is we've got the different age groups for the independent variable differ significantly on a combined dependent variable that consists of all 4 of the DVs we put in. So physical health, mental health, drug use, and stressful life events. So that said, what we now need to do is look to see, well, if we've got a significant difference between the groups on a combined, is it the case that each of those DVs is contributing to that significant difference, or is it just some of them or one of them? So what we would then need to do is kind of do these follow-up tests, and we could do Roy Bargeman's step-down analysis, or we could look at a table of univariate ANOVA results. In this video, I'll look at the univariate ANOVA results first, and then we'll probably run the Roy Bargeman's step-down analysis. Okay, so first thing we're going to do is look at these univariate ANOVA results. We need to make sure we can assume equal variances for each of the DVs individually, and luckily SPSS, because we asked for homogeneity tests, has given us a table of Levene's tests, 1 for each DV. So we need to kind of have a look at this as a follow-up to make sure that each of these DVs in isolation, we can assume equal variances for them, and that will give us some idea of how safe we are to interpret univariate ANOVAs in relation to it, or whether we need more robust tests. So if we look at physical health symptoms, if we use based on the mean, that's kind of your standard Levene's test. So we shall use that for each one of these. If we look at physical health symptoms, we have a Levene statistic of 0.107, p-value of 0.956, so it's not significant. So we're safe to assume equal variances between the age groups for physical health symptoms. If we look at mental health symptoms, Levene statistic of 0.941, p is equal to 0.421. Again, it's not statistically significant, so we can safely assume equality of variances for mental health symptoms between each of the age groups. Use of psychotropic drugs, get a Levene statistic of 2.367. P is equal to 0.70. So again, not significant, so we are safe to assume that there's equal variances between the age groups when we just look at psychotropic drug use as a DV. Stressful life events, though, is our last one, and if we look, we've got a Levene statistic of 4.864, P is equal to 0.002. So in this case, we have got a significant Levene statistic. So for stressful life events, we can't safely assume equal variances. So when we look at our univariate Fs, if we find that stressful life events is a significant predictor, is significantly different for the age groups, we probably need a more robust F statistic to test it against, such as Welch's test. But we shall cross that bridge shortly. Okay, so here is our table of ANOVAs, our test of between subjects effects. It's kind of, it's like it is like your usual ANOVA table. It's obviously just a bit bigger because we've got our variable, our independent variables age group, but we've got 4 F ratios, one for each of the DVs that relate to it. And if we look at this, we can see that for physical health symptoms, we've got an F value of 1.030, P is equal to 0.379. So it's not statistically significant. So this combined, this significant MANOVA result, it doesn't seem that physical health symptoms is significantly accounting for any of the variance between the differences between the groups. Looking at the second one, mental health symptoms, we've got an F value of 1.091, P is equal to 0.352. Okay, so again, mental health symptoms, not statistically significant. Use of psychotropic drugs, we've got an F value of 0.717, P is equal to 0.542. And this time again, not a statistically significant difference between the age groups on that DV. Okay, so 3 of our 4 so far not being significant, so that tells us really that the last one, stressful life events, must be. And we can see there we've got an F value of 15.030, P is less than 0.001. Okay, so that's, if you remember, we're doing 4 univariate ANOVA tests. And because that's multiple testing following a significant omnibus test, significant MANOVA, we need to adjust our threshold of significance, our alpha level, using Bonferroni. And we do that by dividing our usual threshold for significance, 0.05, by how many tests we're doing. So in this case, 4. Which would give us a new adjusted threshold for significance of 0.0125. And if we do that, we still see the others are obviously still not significant, but this one is stressful life events is. So it's, P is less than 0.001, so it's still much smaller than 0.0125. Okay, so what we're seeing here is that on this combined DV is showing us we've got a significant difference between age groups in the MANOVA, but if we look at the univariate F-tests as a follow-up, we can see that the only DV that's really contributing to that difference is stressful life events. Okay, so that's some interesting follow-ups that we see there. So yeah, stressful life events is accounting for most of the difference, or all of the statistically significant difference between age groups. But we've got 4 age groups. So now, although we've done a follow-up test with these univariate F-tests following MANOVA, what we're still left with is we've got a univariate F-test that tells us that there's a difference between age groups in terms of stressful life events. And if we go up and look at our table of descriptives, back up here, if we look at stressful life events and we look at the means, what we see is the highest mean is for the youngest age group, 20 to 30 years, 263.45. And then it goes down for 30 to 40 year olds, then it goes down for 40 to 50 year olds, and it's lowest for 50 to 60 year olds. So all we know is that this highest mean, 20 to 30 year olds, differs from the 50 to 60 year olds. Okay, so that's useful to know in itself, but we'd also like to know if there's a difference between 20 to 30 and 30 to 40, and 20 to 30 and 40 to 50, and 30 to 40 and 40 to 50. So we need some sort of post-hoc tests to be done. And it is worth keeping in mind when we do these post-hoc tests that we got a significant Levene's test. We can't assume equal variances. So we would want to run some sort of analysis with a just using stressful life events, but with a more robust post-hoc test that allows us to where we can't assume equal variances. So we can set that up as a separate analysis. We can go to general linear model, univariate, and our independent variable is still the age groups, but the only independent variable we're interested in is stressful life events. And if we could ask for these tests again, but we've already got them, so we don't need them. What we're most interested in here is post-hoc tests for age group. And we could ask for Bonferroni and SNK and Tukey and the like, but we know we can't assume equal variances. So let's just ask for Games how in this case. Click continue, click OK. That should run the analysis for us. What we'll find is we've got, and now with this univariate F-test, we still get the same ANOVA 15.030, P is less than 0.001, and we can look at this Games-Howell multiple comparisons table and see where the significant differences lie. Okay, so 20 to 30 compared to 30 to 40 year olds, we've got a significant difference. Okay, 20 to 30 compared to 40 to 50 year olds, we've got a significant difference again. P is less than 0.001 in this case. 20 to 30 compared to 50 to 60 year olds, we've got a significant difference again. We knew that was going to be the case because they were the highest and lowest mean. In this case, P is less than 0.001. Now, 30 to 40 compared to 40 to 50 year olds, P is equal to 0.368, so not a statistically significant difference. 30 to 40 compared to 50 to 60 year olds, P is equal to 0.025, so this is a statistically significant difference between the two. 40 to 50 compared to 50 to 60-year-olds. P is equal to 0.675. So what we're seeing here is that 20 to 30-year-olds are significantly different to all the other age groups. 30 to 40-year-olds are significantly different to 50 to 60-year-olds. But the others are not significantly different. So 30 to 40 are not different to 40 to 50. 40 to 50 are not different to 50 to 60. So there, this post hoc test kind of shows us where our differences lie. Okay, so that's pretty much how we would have to break it down. Certainly with this set of results, we checked Box's M-test. We found that it wasn't significant. We interpreted our result using Wilks Lambda. We found we had a significant result. We decided to use univariate F-tests with a Bonferroni correction. First, before we did, we checked our Levine's test and we found that only one of them we couldn't assume equal variances for. When we looked at our test of between subjects effects, it turned out that the one we couldn't assume equal variances for was the only one that was statistically significant in terms of differences between age groups. So the difference on the combined DV and the MANOVA was entirely being driven by this one DV, stressful life events. So to follow that up, we then did post hoc tests to look at where the differences were on that single DV between age groups. And we used a robust post hoc test because we couldn't assume equal variances. So we ran the analysis again and ran a univariate ANOVA using the Games-Howell post hoc test. What we found was that 20 to 30-year-olds significantly higher stress than all other age groups. 30 to 40-year-olds significantly higher stress than 50 to 60-year-olds, but no difference between 40 to 50, 50 to 60, and 30 to 40. Okay, so that is, I'm going to stop this video here and I will do a separate one showing you how to do the Roy Bargeman step-down analysis on the same set of data.